Black holes are the most scary and mysterious objects in the universe, and the James Webb Telescope now has evidence of what the interior of a black hole looks like. We physicists have waited 100 years, since 1916, for this photograph. What exactly did they find in the oldest black hole, and how did they find it? Join us as we explore how the James Webb Telescope just announced the first real image of the inside of a black hole. Black holes are forcing us into a deeper understanding of what space and time are, as black holes are the keys to understanding the universe. There is a lot to be said about black holes, but perhaps the most notorious quality for which black holes are known is that they are extremely mysterious. Basically, black holes are those regions of space where no object, not even light, can escape. The main reason for this is that, by nature, black holes have extremely strong gravitational fields. Because of this, black holes are practically invisible and can only be detected by the way they affect and influence their surroundings. Imagine a specific part of space and imagine everything being pulled into this particular region in an irresistible magnet-like manner. As objects are drawn into it, this region or point becomes so dense that it creates a deep pit in space-time. That is what a black hole is. Essentially, its robust gravity makes it warp the very fabric of the universe. The more intense the gravitational force, the more it bends light and space. Although, as stated earlier, black holes can't be directly visualized like you can see a remote on a tabletop, scientists can still observe them indirectly. For instance, if a black hole is close enough to a star, it instantly pulls out the gas in the star into itself. The gas moves spirally into the black hole, all heated up and glowing brightly. This occurrence is often observed through the help of a special telescope. Also, a black hole is observed to be present when a star moves in an unusually fast and strange way, showing the proximity of a black hole. Although the term black hole might seem like it was coined hundreds of years ago, Princeton physicist John Wheeler came up with the name in 1968. Before it was named black hole, other scientists had called it all sorts of names like dark star or frozen star, and there were reasons for those names. The early conception of a black hole, as we now call it, was that it was invisible and frozen in time. When John Wheeler used it in a lecture, those names were later displaced by the term black hole. People found it more appropriate as a scientific term, unlike dark star and frozen star, which sounded like something out of a science fiction book or something with a magical edge. Black holes expressed what these objects truly are, regions of space where matter and energy, everything and anything, without exception, disappear. Besides, the new term retained the mystery surrounding the object in question. The idea of black holes was actually conceptualized in the 18th century by two different scientists, John Michel, an English clergyman and scientist, and Pierre-Simon Laplace, a French mathematician. With the help of Newtonian gravity, they were able to imagine objects that would be dense and enormous enough to swallow anything, even light. The front-runner in conceptualizing this idea was John Michel. In 1783, he suggested that there might be objects much larger than our Sun, with the ability to pull anything into them. Michel referred to these objects as dark stars, believing that the escape velocity of such a massive star would be faster than the speed of light, making it invisible. Escape velocity is the amount of speed a star needs to break free from its gravitational pull. In 1796, almost a decade after Michel's idea, French scientist Pierre-Simon Laplace elaborated on Michel's idea in his book, Exposition du Système du Monde. Laplace was fascinated by the idea of black holes, or invisible bodies, and thought they could really exist. Although there were no direct observations to confirm their suspicions, thanks to their work, we now have an understanding of what black holes are. But how do black holes form? This is a question worth asking and also worth answering. There are various ways in which a black hole can be formed. The first type of black hole is the stellar black hole. A stellar black hole forms when a star reaches the end of its life cycle and implodes, collapsing in on itself. Typically, they form in stars at least 20 times bigger than the Sun. Like the Sun, every star shines due to the nuclear reactions at their core. However, when a star much bigger than our Sun runs out of fuel, it can no longer support itself against gravity, and the core of the star collapses in on itself. The result? A black hole. The entire process of a star collapsing in on itself is known as a supernova, which erodes the outer layer of the star while shrinking its inner core into an unbelievably small and dense point. The black hole formed from this process has something called singularity at its core. Singularity is a point where the density is infinite and the laws of physics no longer apply. When matter is squeezed into smaller spaces, they necessarily heat up. It's a simple law of chemistry. Stellar black holes are all over the universe. In our galaxy alone, the Milky Way, scientists estimate that there are over 100 million of them. To put it into context, the Milky Way has around 100 to 400 billion stars in total, so having 100 million black holes is an enormous number. Thankfully, these black holes are not crowded together but spread across different places in the galaxy. Also, not all the black holes in our galaxy are active, some are not pulling in material, which makes it even harder to discover them. As scary as stellar black holes may seem, supermassive black holes are even more terrifying. Supermassive black holes can be found at the centers of very large galaxies. In fact, they can be millions or even billions of times bigger than the Sun. For instance, the black hole at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million suns. But this is nothing compared to other black holes in more distant galaxies. Supermassive black holes are formed when galaxy collisions occur. When two galaxies collide, the stars, gas, dust, and all the elements of both galaxies mix together. Most of the time, the result of this collision is that the extremely massive black holes at the centers of both galaxies combine to form an even larger one. This can alter the shape of the galaxy in gigantic proportions. There's still much mystery surrounding supermassive black holes and their formation. Some scientists believe they emerged from seeds, which themselves may have emerged from dense star clusters. Interestingly, there's also a theory that black holes have existed since the advent of the Big Bang. These are called primordial black holes, as they date back to the moment of the Big Bang. It is believed, though not universally accepted, that regions of the universe were so dense that very tiny black holes could have emerged. Many of these primordial black holes might still be floating around, but they are hardly detectable. There are also intermediate mass black holes, which aren't exactly primordial nor supermassive. They vary in size, from very small to very large, but as of now, there's no evidence of them. They remain purely theoretical. One interesting fact about black holes is that they take up zero space, even though they do have mass. Another interesting fact is that black holes can spin, though some do not rotate at all. An example is the Schwarzschild black hole. This is because they don't have a complex structure, they are rather very simple by nature. On the other hand, curved black holes can spin very fast, and they can drag both space and time around them. This brings about the term called space dragging. That said, curved black holes aren't the only black holes with the ability to spin, there are a lot more. Not long ago, the James Webb Telescope discovered something utterly astonishing and groundbreaking. Not only did they find the oldest black hole in the universe, but they also captured the real image inside the black hole. According to them, this recently discovered black hole is 10 times the size of the Sun, and it was formed 570 million years after the Big Bang. Going by this black hole existed when the universe was barely past its inception, and by the current age of the universe, the black hole was formed when the universe was at 4% of its current age. Another interesting but also confounding thing about this black hole is that, given its extremely massive size, the black hole must have grown extremely fast in such a short amount of time. This has staggered scientists and has evoked a lot of questions. Needless to say, the James Webb Space Telescope, JWST, has the highest infrared capability of any telescope in the world. It is the most powerful and surpasses its predecessors. Its infrared ability makes it more than capable of spotting far distant objects, even those that may have been formed right when the universe began. Thanks to this extreme and unrivaled vision, we have now spotted not only the oldest black hole but also the image of its insides. The James Webb Telescope detects black holes in a truly special and highly enhanced way. It makes use of what's called redshift. But what exactly is redshift? To clarify, we need to understand this first. Anytime light travels through the universe, the light itself changes and is never the same. This is because the universe is always expanding, and as the universe expands, so do the light waves. The light waves stretch out, becoming longer and shifting toward the end of the spectrum, which is usually red. This is what has been termed redshift. From the moment light leaves its source, it becomes more redshifted due to the continuous expansion of the universe. The implication of this is that redshift can tell us two things: 1, how far something is, and 2, how old the light we are seeing is. But the question still remains, how does the James Webb Telescope utilize redshift to find black holes? Before answering, let's clarify these details first. Black holes do not emit light themselves. They are invisible and have super strong gravity that nothing, including light, can escape. But black holes attract gas and dust very speedily whenever either gets too close, and the matter starts moving extremely fast due to the pull. This consequently leads to extreme heat in the matter, which begins to glow brightly. It is the light of this glowing material that the James Webb Telescope looks out for. The telescope analyzes how much the light has been redshifted to understand the distance of the black hole and the time the light was emitted. This was how the James Webb Telescope discovered the black hole. It detected a redshift of 12.5, showing that the light emitted from a far distant galaxy was stretched by a factor of 13.5. This redshift is the highest ever recorded and dates back just a couple of 100 million years after the Big Bang. This discovery has illuminated questions surrounding the conditions of the early universe. Besides that, the discovery also hinted at the galaxy being surrounded by prodigious amounts of gas and dust, most probably falling into a supermassive black hole. As the gas spiraled inwards, a swirling disk, also called an accretion disk, began to heat up as it neared the black hole, producing intense radiation. Some of the radiation spread into space, while some was absorbed by the surrounding gas and dust. The absorbed radiation was emitted again as infrared light, which the JWST could detect. More than anything, this discovery by the James Webb Space Telescope has brought us truly refreshing insights into that ancient black hole. By assessing the light being pulled and attracted by this black hole, the JWST can reveal a lot that needs to be known about this whole saga. Based on the telescope's observations, the black hole is over 10 million times larger than the Sun in our solar system. The accretion disk, a swirling ring of dust and gas, is so hot that it was calculated to reach up to 1 million degrees Celsius, the highest level recorded. This discovery is such a milestone for many reasons. The first is that it adds to our repertoire of knowledge about space while solidifying some things we've already known. Also, now that the JWST was able to trace the oldest black hole discovered, we might finally understand how the universe was formed, how the first stars, galaxies, and earliest black holes came about. Additionally, this discovery is revolutionary in changing our perception of how big a black hole can be. Before this discovery, it was understood that black holes normally take billions of years to grow to such enormous sizes. However, this discovery suggests that there may be certain factors yet to be accounted for that are responsible for their sizes, sparking a wave of new theories and speculations. Quite interestingly, there have been speculations about how influential a black hole this big might be in relation to the galaxy hosting it. The star formations of the galaxy, as well as its overall dynamics, are thought to be likely influenced by the presence of this black hole. Beyond observing distant galaxies, black holes, and other interior secrets of space, the James Webb Telescope has also been crucial in shaping our understanding of the universe's history. Not only can the changes in black holes over billions of years now be known, but the JWST doesn't do this work alone. It operates with the collaboration of other powerful telescopes located both on Earth and in space. The JWST is only effective thanks to powerful X-ray telescopes such as Chandra and XMM Newton, which are highly skilled at detecting high-energy radiation. With these telescopes, all processes and events around black holes can now be understood. Additionally, radio telescopes like ALMA, which specialize in mapping jets and outflows from black holes, complement the work of the JWST. This collaboration is fortified by data from other missions like Planck, WMAP, and Euclid, whose studies revolve around the structure and evolution of the universe. The JWST also aligns its findings with what Hubble and Spitzer have established, ensuring foolproof understanding in terms of galaxy formation and growth. In fact, the JWST has enhanced our knowledge of planets, both within and outside our solar system, while working alongside missions like TESS and Kepler. Another fascinating discovery made by the JWST is related to supermassive black holes. The JWST has discovered molecules known as polycyclic aromatic hydrocarbons, PAHs. These molecules, made of carbon and hydrogen atoms arranged in ring-like forms, exist in almost every part of space and contribute to cosmic processes. This discovery is astonishing because pars are widely regarded as fundamental building blocks of life. Life cannot exist without them, and they also play a role in forming stars and planets. When pars are exposed to light, specifically ultraviolet light emitted by stars, they project a unique infrared light. The JWST has helped us understand these molecules more, especially in terms of their size, shape, charge, and temperature. What's interesting is that pars are located very close to supermassive black holes, a place no one would expect them to survive due to the intense radiation. One would think these molecules would be destroyed, yet they persist even in these extreme environments. This finding has really changed the outlook on space and life in itself. The JWST discovered them in 3 particular galaxies, NGC 6552, NGC 7319, and NGC 7469. From Earth, the galaxies are between 200 and 370 million light-years away. Although that seems extremely distant, they were not too far and not out of reach for the JWST. The discovery was made during a program called the AGN MIRI Guaranteed Time Observations. The aim of the program was simply to study every single active galactic nucleus, AGN, which are the very bright centers of galaxies that are powered by supermassive black holes. As stated earlier, most scientists thought that pars could not survive in high radiation environments. The reason was that they believed their proximity to supermassive black holes would break them down into smaller bits or molecules. The discovery came as a shock to them. The way this discovery revolutionized our understanding of different things cannot be understated. First, it goes to show that JWST is so powerful, in fact, superior to other telescopes. Only the JWST was capable of unearthing such unthinkable secrets. Also, the scientific understanding of supermassive black holes has been altered. After the discovery, it became evident that supermassive black holes are not just agents of destruction, but they are in fact agents of survival, with the way they have enabled complex molecules such as the pars to survive and thrive. Clearly, the JWST will be crucial in the long term, and there is still much left to be explored in space. When you're in an open field or lying face up, looking at the sky and the thousands of stars at night, remember there is still a lot to discover from space, only that it will take many thousands of years, if not millions, to uncover them. So, do you think the James Webb Telescope would find more black hole interiors? Let us know your thoughts in the comments below.